So, so today I'm going to do some presentations about some of these questions. There were some very nice solutions posted by some of you yesterday, and I'll talk through some of them. I'll invite some of you to do presentations as well. Like some of the solutions are somewhat subtle, so I want to make sure that they're repeated in Chinese. So I'll be asking some of you to come and do presentations. That does mean we'll be going a little bit slower today. Okay. Anyway, so question number one was primarily computational. So while it is interesting and important, I'm going to maybe discuss it if we have time later or on Thursday. Let's move on to question two. Let's start with question two. Okay. So what is question two about? Let me show this question to you visually. So let's say there are three people. There's Alice, Bob, and Eve. So what does Alice have? Alice has a message M. So she has a message M that she wants to send to Bob. But if she just sends this message to Bob, then Eve will hear this message, and that would be a problem. So you don't want Eve. So we often call this person Eve because Eve is the eavesdropper. So it's just a silly little joke. Eavesdropper for Eve, right? So anyway, so we want to hide the message from the eavesdropper. We want to make sure that the eavesdropper Eve does not learn the message. So what can we do? Well, luckily, in advance, Alice and Bob have shared some secret. So what is a secret? The secret is something like common randomness, let's say R over here. Okay, so there's some common randomness R that both Alice and Bob know, but Eve doesn't know. Okay, so this R, let's say, is uniformly random over something. So I'm going to use Jianqiu's solution over here. So and she'll be describing her her solution. So so I'll use the notation that she's implicitly using over here. So let's assume that this R is uniformly distributed over a field with n elements. So let's imagine that n is a prime or a prime power. Okay. So this R is uniformly distributed over this finite field. Okay. For example, it could be just a bit, n could be just 2 as an example. Okay. So there's a random bit. And similarly, Alice's message has some distribution. This could be uniform, it could be non-uniform, it could be more complicated, like it could be English language. So in the English language, not all messages are equally likely, right? Like the QWXZY is not a very likely message to send in the English language, whereas hello is a much more likely message to send in the English language. So the probability distribution of M is much more complicated. But in the example that Jianqiu is using, so over there, just for example, only for example, she assumes that this M is also uniformly distributed over Fn. Now this is only an example. This is strictly necessary. This is only an example. Okay, just to highlight that. All right. So now, in the example that Jianqiu gave, so first of all, what does she note? She notes that because of Bayes' theorem, so Bayes' theorem is an elementary probability theorem in probability that you've probably studied in your secondary school. It says that if you have two random variables, in this case, let's say M and X, then the probability of M given X is the same as the probability of M times the probability of X given M over the probability of X, right? This is, you've studied this theorem, I think, hopefully in probability. So now here, this is an example of one potential scheme that could be used. Okay, so let's go back to the figure and see what is happening over here. So in this case, now Alice has this message. She can't send it directly to Bob, but she could encode this. So she could transmit some function X which is a function of m and r. Okay, so as an example, maybe the first example is that this x is equal to m plus r, where this plus is the usual addition over real numbers. Okay, so it could be, oh actually let me zoom in so you can see a little bit more clearly. It could be that one potential thing that Alice could do could be that she sends x is equal to m plus r, and at least for Bob this is good enough because Bob knows r, so Bob knows r, and if he sees x then he can do x minus r and get m, right? So at least Bob will understand what Alice is saying. But the question is, if Eve sees this x, does Eve learn anything about m, about the message? Okay, so just as an example, suppose n is 2, and this over here as well, the message is also a bit. So this is also from F2. So Alice has a bit and they have a bit of common randomness. So let's see what happens if we do this. Okay, so if we do this, then you're going to send x is equal to m plus r. So the probability, so x could take three possible values, right? X could take three possible values, 0, 1, and 2. The probability that x is equal to 0 is happens with probability 1/4. The probability that x is equal to 1 happens with probability half. The probability that x is equal to 2 happens with probability 1/4, right? Now let's ask ourselves, suppose 2 is transmitted, suppose x is equal to 2 is transmitted, and Eve sees this, then in this case, what happens? Well, Eve sees 2, so Eve sees 2, so now what is the probability of m given x is equal to 2? Okay, so in particular, the probability that m is equal to 0 given x is equal to 2. So if Eve is seeing 2, the only way that could have happened under this encoding scheme, under this way that Alice chooses x, is if m is 1, right? M cannot be 0. If Eve is seeing 2, then m cannot be 0, right? Because of that, this probability, the probability that m is equal to 0 given x is equal to 2, is not equal to the probability of m, right? Like if the original probability of m is half or something else, then after Eve sees something, it is no longer random for Eve. Eve has learned something, right? So therefore, this is not a good scheme. This scheme would give Eve some information over here, right? Whereas we want to hide the information from Eve, but this scheme is giving Eve some information. Okay, and in the solution given by Jianchu over here, she does another example where, let's say, both m and r are, let's say, uniform from 0 up till n minus 1. Then she computes. So first of all, she computes the probability. She computes the probability of yeah, okay. So before going there, so what do we really want? The question asked us, the question demanded, let me say this, so the goal from Eve, or the goal for goal with respect to Eve is that we want the probability of m given x to be equal to the probability of m, right? What is this saying? This is saying that initially there is some probability distribution over m, right? Maybe m is half, like m equals 0 with probability half, m equals 1 with probability half. And then even after Eve sees x, we want the probability of m given Eve's observation x to stay the same. That's what we are desiring, right? We're desiring two things. One, we want that Bob can decode m. We want that Bob can figure out what m must have been, and that was okay with the m plus r, x equal to m plus r. But the second goal is not true, right? The second goal, that the probability of m given x is the same as the probability of m, is not true over here, right? So, and just as another example, so Jian Chu has given an example over here where she, oh, I'm sorry. So let me say one more thing over here. So now using Bayes' theorem, the probability of m given x is equal to the probability of m times probability of x given m over probability of x. So if we want that the probability of m given x is equal to the probability of m, what must be the case must be that the probability of x given m is equal to the probability of x, right? The only way that the probability of m given x is equal to the probability of m is if this ratio is 1, which is saying that we want the probability of x given m to equal the probability of x, right? That is the only way that you can meet your desired goal. Okay, so if that is the case, let us compute the probability of x under this scheme when x is equal to m plus r. Okay, so when we compute this, so Jian Chu computes this and she gets 1 over n square when x is 0, 2 over n square where x is 1, all the way till n when x is n minus 1, and then it decreases again. I think this is a typo. This should be n. Sorry, this should be. Oh, sorry. No, this is fine. 1 over n square when x is 2n. Sorry, 2 times n minus 1, right? Because so small typo. 2 times n minus 1, because that's the maximum value that x can take. Okay. So this is not a good scheme. However, and this is different. So the probability of x, therefore, is different than the probability of x given m, because the probability of x given m, if you know m, so let us see this calculation directly. So the probability of x given m, is equal to the probability of, so what is x? X, remember, is m plus r. So the probability of m plus r given m, which is the probability of m given of r given m, but r is independent of m. The randomness here is independent of m, so this is just the probability of r, right? And the probability of r is uniform, right? So that's a quick way of seeing this calculation that Jian Chu did over here, which is in this case the probability of x given m is uniform. It's 1 over n. So clearly these two quantities are not the same, right? So this is showing that this is a different way of showing that this addition scheme does not meet our desired goals. Okay, but one scheme does work. What is the scheme that does work? So a small change, instead of adding over real numbers, instead of adding this m and r over real numbers, what if we add them over a finite field? Okay, what if x is defined as the summation of m and r over the finite field? In this case, you can do the calculation again, and the probability of x will turn out to be 1 over n for every value of x over here, x going from 1 up till n minus 1. Okay, so therefore the probability of x will be the same as probability of x given m. Therefore this ratio, probability of x given m over probability of x, will cancel out, and therefore you will have that the probability of m given x is equal to the probability of m. Okay, so this calculation over here is very nice. You can actually show that this is true not just in these examples, but regardless of what the value of the probability of m is. Regardless of what the value of the probability of m is, the probability of x given m will always be 1 over n. The probability of x will always be 1 over n, and the ratio will cancel out, and therefore you will have this equality over here. Okay, so now multiple things to say over here. So Jian Chu and if both of you, okay, looks like both of you want to come, maybe, right? So I'm going to repeat some important points over here, and then they will help repeat this in Chinese, because well, the majority of the class speaks Chinese, and I do want to make sure that these subtle points are repeated. Okay, so guys, are you paying attention? I'm going to make some points in English that I would like you to repeat in Chinese. Okay. holding hands, very nervous. It's okay. It's okay. You did a good job writing the solution, and I'm sure you'll do a good job presenting. Okay. So we'll do it step by step. I won't say everything, so you'll have some chances to say whatever. Okay. So first of all, we want to make sure that the system diagram over here. This is called a system diagram. There's a system, and this diagram shows the system. The system diagram is explained well. Okay. And the TA will help you as well if you get stuck. So there are three people: Alice, who has a message; Bob, who wants a message; Eve, who is the eavesdropper, and we want to hide the message. This message is M, and Alice and Bob have some common randomness, some shared secret, which is, let's say, uniform over a field. For example, a field with just two elements, right? Like a binary field. This message may be uniform over this field, or it may be arbitrary, right? It need not be uniform over this thing. Like, for example, in the English language, it could be, well, the probability of English words is much higher than the probability of non-English words, right? So it could be arbitrary over here. If Alice sends the message directly, then Eve will listen, and that's not good, right? So, but what do we want to do? We want to do two things. We want to make sure Bob understands the message, and we want to make sure that Eve does not understand the message. That is to say that the probability of x given m should be the same as the probability. So the probability of x given m should be the same as. Let's write this down over here. So the goal with respect. Oh, right. So the second goal is this one: the probability of m given x. My mistake. The probability of m given x should be equal to probability of m. We want that. Okay. So it's a lot to say, but I just want to make sure that the question is well understood. Okay. So can you repeat all of this? In Chinese?
就是这个题，就是说，Alice 要传给 Bob 一个 message，就是那个 M， 然后他们在传输的过程中，他们传输的内容会被那个 Eve 去偷听到，然后如果被偷听到的话，你就失败了，然后所以他们就试图去给这个message 加密，就是用 R 去加密，然后 M 和 R 进行一些操作以后，然后它反映出来的就是那个 X， 就是 Eve 只能会看到 X， 然后 Bob 因为他也知道你给定的那个 R， 然后也知道他们要进行怎样的操作，所以他就能解出来那个 M。然后这个题它需要你最终达到的那个要求是在给定 X 的情况下，你能猜到 M 的那个概率和你直接猜 M 的概率是一样的。
Okay, good. Kalia, do you want to do the next one?
Okay.
Okay, good. So now Kalia is going to help with the next one, and she was like, okay. So now let's first look at a scheme that does not work, just to understand what the challenge is. Okay. So the scheme is, let's say x is equal to m plus r, where the plus is defined as addition over the real numbers. Okay. I'm sorry, I again forgot. So first, let's describe Bayes' theorem. So to make sure that the probability of m given x is equal to the probability of m times the probability of x given m over the probability of x. And our goal will be met if the probability of m given x is equal to the probability of m, if this ratio, probability of x given m over probability of x, is equal to 1, right? If this ratio is equal to 1, then our goal will be met. So suppose we say x is equal to m plus r, and as an example, let's say that m is uniform over 0 through n minus 1, right? Then in this case, we can compute the probability of x. We can just count the number of ways that you can get x is equal to 0. That's just one way. The number of ways you can get x is equal to 1. There's two ways: 0, 1, 1, 0, and so on. So you can do this calculation, and you can see that it is not uniform over here. But the probability of x given m, one way of seeing that it is uniform is by doing this calculation that I did over here. The probability of x given m is the probability of m plus r, because x is just m plus r given m. Now, if you know m, then the probability of m plus r given m is the same as the probability of r given m, right? If you know m, then the probability of seeing m plus r given that particular value of m is just the same as the probability of r given m. Right? Kalia is thinking about this. Jianshu is nodding. Right? Okay. so if you have trouble, Jinshu can help you with this step, okay? And then R is independent of M, so this is just the probability of R, right? And R we said is uniform from 1 through n minus 1, right? So therefore, because of this, this is a shortcut way of calculating the probability of x given m, right? Okay, so the goal for do as much as you can, and then Jinshu will help you and the TA will help you. But the goal is to show that two things. Firstly, Bayes theorem, right? The context of Bayes theorem, and then if the ratio is 1, then our goal is met. And secondly, to show that this example scheme x is equal to m plus r works for Bob, but doesn't work for Eve. Okay, works for Bob. So Bob can figure out m knowing x and r, but Eve will may learn a little bit about the message.
就是 x 和 m 之间有一个关系，是 x 等于 m 加 r， 然后有一个公式，就是在已知 x 的情况下 m 的可能性等于在已知 m 的情况下 x 的可能性乘以 m 的可能性除以 x 的可能性。然后现在就是比如说 m 是0到 n 减1里面任意取一个， r 也是0到 n 减1里面任意取一个，那么 x 等于0的可能性就是相当于 m 取0 r 取0，就是 n 分之一乘以 n 分之一是 n 方分之一，然后如果 x 的要等于1的话，就相当于m 等于0 r 等于1，或者 m 等于1 r 等于0，所以是两种，就是 n 方分之2，然后用这样的方法就可以求出就是在实数，如果它们是实数相加的情况下，就是 x 所有的可能性，然后第二个就是老师想让我解释的，就是如果在已知 m 的情况下 x 的可能性就相当于 m 已经确定了，然后相当于r 从0到 n 减1里面任意取一个，所以是 n 分之一，就相当于从 n 个里面取一个出来，所以最后 x 的可能性也是 n 分之一。然后接下来没有你说解释了，没有，可是这个最后那个
老师刚才那个给的那个式子，就是说，就是因为 x 就是 m 加 r 嘛，就是后来就是算了一下已知 m 下 x 的概率，然后把 x 换成 m 加 r， 然后因为 r 和 m 是独立的，然后已经给定了 m， 在已知 m 的情况下 m 加 r 的概率就是已知 m 下 r 的概率，然后它们两个独立就直接是求 r 的概率就可以了。
Very good. Okay, now final part of the explanation, not done yet. So now we have seen a scheme that does not work, but a simple change makes it work, right? And what is a simple change? Instead of doing x is m plus r over real numbers, if we do x is equal to m plus r over finite fields, so then you can calculate the probability of x again, and in this case, for every value of x, you can calculate the probability of seeing x, the probability of seeing that particular x is going to be 1 over n. It's going to be 1 over n for every value of x, which is the same as the probability of x given m, which is 1 over n. Therefore, this ratio cancels out, and therefore we have the desired equality, right? So, and in your explanation, also describe why the probability of x is 1 over n for every value of x.
然后之前那个样子就不符合要求，然后就给它再加上一个条件，就是这一系列的变化都要在那个finite field fn 里面进行，然后就会把上面那个 x 各种值的那个概率，就是因为当它到n 的时候 ，x 等于 n 的时候就变成 x 等于0了嘛，然后就把它们对应的互相加起来，然后就会发现加起来，x 就属于0到 n 加1，然后它们的概率都是 n 分之一，然后这个事情就解决了。最后就求在 x 下 m 的概率，然后就是后面那个等式里面上下那个后面那项都是 n 分之一就消掉了，然后就得正。
Good solution. Wow. So this was the calculations are not so bad, but sometimes the subtlest questions, like the questions which are the most complicated, are not the ones in which the calculation is hard, but in which the understanding is hard, right? And I think they did a really good job, right, in this very subtle question. I see people nodding. So let's clap and make sure that they see our appreciation. Okay. And remember, you'll be able to ask them if you still have questions, right? All right, good. Eric, we're going to do another one, so I'll need your help again. Okay, so yeah, I mean, we're going slowly today, but that's okay because these are complicated questions. I want to make sure at least some of the beautiful ones, people get a chance to see the solutions to these, okay? So this one is question 3. So let's see question 3, and I'm going to ask Alex to come and help describe, okay? So Alex, can you come? So what is the question over here? So the question, let's look at a figure drawn over here. Okay, fine. So first, let's look at a couple of examples. So firstly, this is the example already in the sheet, but drawn visually. So what is the question? The question says, what does geometry actually mean if we think of geometry just like sets? Okay, so let's think about that. So what is so the usual geometry that you guys are used to thinking about is, you know, you have, let's say, a plane. So a plane is a collection of points, and you have lines in the plane. So lines in the plane are sub collections of these points, right? They're subsets of points. Now, what do we require from the usual geometry? Well, as in the usual geometry, given every 2 distinct points in the plane, there is exactly one line that contains both the points, right? This should not be surprising. We are used to this, right? We're used to thinking about given 2 lines, given 2 points, there's a unique line which joins those 2 points. Okay, but even if it's a finite set, we're going to demand that every collection of subsets that we will call a line should have the property that there's a unique subset. There's a unique subset that contains 2 given points. Okay. Secondly, given a line and a point not in that line, so given a subset and a point outside that subset, there is a unique other subset that contains that point and which does not intersect that line. Okay, so this is basically saying that there's a unique parallel line that passes through the point P that is parallel to the original line, right? Again, you're used to this in the usual geometry, but now we are demanding a property of subsets, that these 2 subsets do not intersect, but the second subset contains the desired point, right? And then the third thing is just demanding that somehow it's demanding that this thing be non-trivial. Okay, if we did not have this requirement, then even a single line would fit the requirements. Okay, so I mean, you have to think about what happens if you don't demand this, but it just becomes somehow trivial. Okay, so let's first see just as an example that the example given here, where the plane has just 4 points A, B, C, D, and there are 6 lines over here, AB, AC, AD, BC, BD, CD, satisfies these 6 conditions. Okay, and one way of seeing that visually is to see the solution posted over here. Okay, so we have 6 points, we have 4 points, we have 6 lines. So this, and the line BD and the line AC are said to not intersect, right? Because visually they're not intersecting in one of the 4 pre-specified points. So we will claim that they do not intersect. Okay. So now you can just by inspection check, firstly, that given any 2 points, AB, AC, AD, or any other pair of points, there is a unique line joining those 2 points. Secondly, given any line, like for example AB and a point not on that line, for example D, there's a line which is parallel to that, right? Similarly, for example, given AC and a point not on it, for example D, then BD we will say is parallel to AC, even though it does not look parallel to AC, but by definition, by claiming that these 2 lines are not intersecting, they end up being parallel, right? And thirdly, we can check that AB, AC, like these 4 points, A, B, C, D, are not on the same line, right? Because our lines are only 2 points, so 4 points cannot be on the line, right? Okay, so the two things, so let's do this in steps. So now Alex is going to do the following two things, right? So he's going to first of all describe to us, he's going to, sorry, not here, he's going to describe to us what the question is saying. So the question is saying in terms of sets, it's repeating in terms of sets, the thing that we used in geometry, right? And then secondly, he'll explain to us the example, which is already in the question, right? Okay, so begin.
我的普通话有点烂，所以不知道大家听不听得懂。就是说这个题目就是说如果我们要在一个 finite field 里面要 define geometry 的话，会是怎么样的事？就是像define 一些set 或者是 subset， 就是一些 points or lines。所以就是说，我们这个题目就是说，如果在这个 finite field 里面，如果我们有一个 subset x 是叫做 points 的话，然后有另外一个 subset L 是叫做 lines 的话，他们如果符合他们如果 satisfy 以下3个条件的话，他们就可以叫做是这个 finite field 里面的geometry， 就是说如果我们想象成在普通的 geometry 里面我们有2个 points， 2个 points 里面一定有一条线可以连成这2个 points， 然后那一条线就是我们那个 line 那个 subset 里面的一个 element， 然后第二个条件就是如果我们有2条线，其中有一点在第一条线里面，我们叫line 1， 然后另外一条线没有那个 point， 我们叫 line 2， 那如果它2条线是平衡的话，那只有一条线是跟原本有那个 point 那条 line 1是平衡的，就只有 line 2。然后就第三个条件就是一个我们怎么说了？就是一个 non-trivial 的property， 就是说如果我们不是如果因为只有前面2个条件的话，我们可以用一条直线就可以画成这个整个图了。所以如果我们有了第3个条件的话，就我们就不能只是用一条线去画整个图，所以就符合这3个条件的话，就可以叫做是一个 geometry。
Okay. Wait, and then you're going to describe this example here.
这 example 是从那题目里的 example， 就是这是如果 q 等于2的话，就会那个图就会是这个样子。我们因为这个图其实我们是看来就像我们平常看的那些 geometry 的图，所以我们比较容易理解。就是如果它的 q 等于2的话，其实我们也可以用我们平常那个 coordinate system， 就是画成4个点，所以它会有4个点。然后我们如果把那些点与点之间连起来的话，就会有6条线，就是你可以画一下，就其实每一个点独立也会有点与点之间就独立会有一条线，就是像同学写了出来一样。然后如果我们先检查一下的话，就我们可以看到，就第一个条件就很容易就符合，就因为每2个点之间都只有一条distinct 的线，所以这就符合了。然后第二个条件就我们是看平衡线，就是你可以很容易看到其实我们找2条线，然后 找其中一点在一条线上面的话，我们可以看到只有一个线是符合这个条件的话，就是说只有如果我们看怎么说这让我想一想，就如果就我们比如说就拿线 AB 来说，就是如果点 A 在线 AB， 但是我们如果拿线CD 的话 ，CD 是跟 AB 平衡，但是我们可以看到就是其实只有线 CD 是跟 AB 平衡的话，如果我们拿了点 A 和线 AB 做比较的话，因为我们看到其他的线都会跟 AB 有连接或者是什么，所以我们只有一条线是跟线 AB 和点 A 平衡的。然后我们看这个图就很容易看到第三个条件，就是说我们看到如果我们有三角形或是四角形的话，其实也符合刚才第三个条件，因为如果你想一下的话，就那个条件是说没有三个点是在同一如果给了4个点的话，没有3个点是在同一条线上面，看这个图也非常容易看到，因为如果有3个点在同一条线上面的话，就没有三角形的出现，应该是。然后如果我们在这个图里面画的话，其实你也可以看到4个点其实不在同一条线上面，所以我们可以看到这个例子符合那个 geometry 的条件，所以它就是在那个q 等于2的时候是一个 geometry。
Okay, wow. So hopefully at this point, at least the question is clear. Okay. Now let's see the magic of finite fields in action. Okay. And yeah, we just have 6 minutes. So let's see how much we can get across in 6 minutes. So this is an example of a plane and lines in just for just 4 points. But actually, anytime you have a finite field, so anytime you have a finite field with q elements in it, with q elements where q is any prime power, then you can define a corresponding plane geometry with q square points and q square plus q lines that satisfy these conditions. Okay. So, and how do we do this? We do this using finite fields and using algebra rather than trying to draw pictures. Okay. So let's look at so even though we said we'll do it using algebra instead of pictures, let's look at this example over here with 3 square, which is 9 points. Okay. And 9 square, so 3 square 9 plus 3, so 12 lines. Okay. And these lines are very strange. Like drawing them, you have to imagine what these look like. But every line over here is going to have 3 points. Every point will be in I forget how many lines, but there'll be 12 lines and 9 points. Okay. So what do? We use the tricks that we've learned from real geometry. So in real geometry, one way of algebraically classifying a line is to write an equation for it, right? Is to write a linear equation for it. So the linear equations for these 9 points. So first of all, we can imagine these 9 points as being indexed by, and I think it was written in another solution over here. Where was it? Yeah. So as being indexed from P00 up till P q minus 1 q minus 1. Okay. So one way of thinking about that is there are q square points over that, and the x and y coordinates are respectively the so every point is indexed by a x coordinate and a y coordinate, where the x coordinate is a finite field element and the y coordinate is a finite field element. Okay. So now we have, okay, so at least we have the points, the right number of points, and we have given them some coordinates. Next, we have to define lines, and to define lines, we will just use linear equations of the same kind that we use for the usual geometry as well. Okay, so for example, x is equal to 0, x is equal to 1, x is equal to 2, y is equal to 0, y is equal to 1, y is equal to 2. So these are the lines parallel to the x and y coordinates that we normally have, plus also the tilted lines, right? Y is equal to x plus 1, y is equal to x plus 2, and so on. So how do we do it systematically? Basically look at all possible lines of the form y is equal to m. I'm just going to change here so you can see what's going on. So y is equal to mx plus c. So first of all, the x is equal to 0, 1 up till q minus 1, because we want to include lines where the coefficient of y is 0. So we want to include things where the coefficient of y is 0, right? And then separately, we can also include lines where this m can take any one of q minus 1 values, and then this can take correspondingly any one of q minus 1, any one of q possible values, and this can also take any one of q possible values, right? So therefore, there are q such possibilities, and then another q times q, so that's q square such possibilities, right? And every one of these is going to define a line, okay? So that's our definition of lines. Now we need to check three things. What are the three things we need to check? Firstly, given any 2 points, they define a unique line. And again, there are multiple solutions. So let's look at Alex's solution. So given any 2 points, x1, y1 and x2, y2, there will be a unique line that satisfies that. There'll be a unique line that satisfies that. Maybe a different way, like I think there's a different solution posted down here as well. Oh, I see. Sorry. So right. So this is a proof by contradiction. So if you substitute these points into two different lines, you cannot get two different values of m1 and m2, right? Or another way of doing it is, if someone gives you 2 points, x1, y1, x2, y2, you can write the usual equation, which I think someone did over here. Yeah, so y minus y1 over y1 minus y2 is equal to x minus x2 over over x1 minus x2, if it can be defined, as long as the denominators here are non-zero. If they're zero, then you have to take it to the other side and so on, right? The usual trick. But you can define a unique line going this way between x1 and x2, right? That's the first condition. The second condition is that given a line, you can and a point not on the line, you can find a unique line which is parallel to that original line and does not pass through it. So again, Alex here has an algebraic solution for that, and then he has we are basically out of time. So here's what I'm going to request. I'm going to request that Alex finish this proof via video. Is that okay? Like, you can record a short video and post it on Piazza. Very good. So basically, the third part he can also prove via by looking at these 4 points, and you can check that these 4 points are never on the same line. Okay, so let me just say one more thing in English, and then I'll ask Alex to very quickly in 1 minute also summarize in Chinese. Okay, so to summarize, what is the idea over here? That geometry is really a statement about sets, a statement about a set of all possible points and subsets of the set which define lines. And these subsets have to satisfy certain properties, intersection properties, non-intersection properties, right? So that's one way of thinking about geometry. The other way of thinking about geometry is via equations, right? So by saying that a line is just a set of points satisfying a certain algebraic equation, right? And once we have this object called finite fields that we understand, then we can write equations over finite fields, and then those give us nice properties about geometry over finite sets as well, right? So in this abstract way, you can then show that certain sets are can you repeat this?
所以 Professor 就是说，如果这道题目就是我们讲那个 finite field 的geometry， 如果我们是要找那个 geometry 的话，我们有两个方法，就是第一个就是我们用一个 set 和 subset 的概念去找那个方法，就是找它有那个 intersect 的特性，还有线与线之间有平衡的特性，我们也可以找到。另外一个方法就是用我们定义一个 equation 去表达那里的点和线，就是如果我们那些 equation 我们定义的那些 equation 符合也可以符合那个intersect 还有not intersect 的特性的话，就也可以表达那个 geometry， 所以就是这样子。
Okay, very good. So today's class is over. Alex will shoot a video just describing his solution in a little bit. So parts A, B, C. I think that those three are important, right? Not necessarily the part that we talked about earlier, but these three things. Okay. Okay, so again, let's thank him because this is non-trivial, right? It requires some very deep and abstract thinking. So let's thank Alex for this as well. All right. Tomorrow, because these are also non-trivial and require some explanation, so we'll discuss briefly questions 4 and 5 tomorrow. Maybe we'll have a question 6 posted by then as well. Do try question 6, the Piazza bonus point question, but we'll discuss questions 4 and 5. And I'd like to request tomorrow Young and Mike to help with the presentations tomorrow as well. Okay. But other than that, class is over.